Okay, so now let's talk about another common process in air conditioning, which is called adiabatic mixing of moist air. Right, so when I say adiabatic, simply means that no heat is lost or no heat is gained, no heat gain or lost. Okay, so this is one of the common process in air conditioning. Like for example, we have two. Let's say we have this ducting right here, and then it converges to another. Let's say another ducting, air ducts, and then exits into one passageway. Let's say here's our air entry, let's say, or airstream 1, and we have this airstream 2, and therefore we have this airstream 3. And somehow there's going to be mixing of this air at point 1 and air at point 2. So it could be that they have different properties. The airstream at 1 will have different properties from airstream at 2, and somehow at the end, what's going to be the properties right here after the mixing. So that's one way, but there's also, this mixing process can also be modeled for infiltration air. Right, so let's say here's a tunnel ventilated poultry house, and we have evaporative cooling pads right here on this end, and on the other end we have ventilation fans. So in top view, this is the pad end, and right here we have the fans, ventilation fan. So airflow will be coming from this side and then exits on the fan side. Right, so that's the evaporative process. But when we talk about air tightness, sometimes the building is not that super tight, and therefore there's going to be infiltration air, or there's going to be air entering on the let's say on the leakage or on the unintended openings. Right, so if it's, let's say a curtain sided walls, so sometimes there's going to be leakage right here. So there's going to be entry of air in that unintended openings. So somehow there's going to be mixing, right? So somehow it can model this mixing process. So one would be the intended path through the pads, and the other one, the other airstream, is through this infiltration. So therefore we can write here, maybe this one is through through the pads, and here would be through the infiltration air. Alright, so that's also one modeling for the mixing. Okay, so now if we analyze this, let's say here's our path, and since it's adiabatic, then we can just put some insulations here for the illustration. Alright, so let's consider our system. Or system boundary. Alright, so here's one entry, and let's say this is point 1, and here's our point 2, and here's our point 3. So at point 1 we have mass of air, or mass flow rate of air, and there's going to be moisture content for that air, and there's also going to be enthalpy of air. Okay, so for this, we also have the mass of air. Let's just write MA2, mass flow rate of air, or airstream 2, and then we also have the moisture content, and we also have the enthalpy. And when they mixes, or when they converges here and mixes, then the end properties would be, let's say, MA3, and we also have this moisture content in this state, and we also have the enthalpy, right? So if we do a mass balance for this, by the way, if we draw the psychrometric chart for this, by the way, for the psychrometric chart, it looks something like this. So let's say here's our point 1 and here's our point 2. So the mixing would be something like this. Right, so it follows, or it is assumed or approximated by this straight line, and somehow the properties at point 3 would be somewhere in between, right? So that's the process. Okay, so for the energy balance, or first maybe we'll do mass balance. So mass balance for, let's say, mass balance 1, or for dry air. Right, so for the mass balance of the dry air, this is MA1, MA2, and MA3. So all the masses that that enters the system is equal to the mass that exits the system. Therefore, MA1 plus MA2 is equal to MA3. Okay, so next one is, let's do a mass balance, but this time for the vapor. Right, so water or moisture. So for the moisture at point 1, this is MA1 times the humidity ratio. So MA1 times the humidity ratio, right, plus the mass flow rate at 2, MA2, times the humidity ratio at point 2 is equal to MA3 times the humidity ratio at 3. Okay, so what else? For the energy balance, so that's going to be MA1 times the enthalpy at 1 plus MA2 times the enthalpy at 2 is equal to actually MA3. However, MA3 is equal to this, so we can write this MA3, or MA1 plus MA2 times the enthalpy at 3. Right, so if we rearrange this, or if we do the math, we can actually express this in terms of something like MA1, or the ratio of the mass is equal to H3 minus H2 all over H1 minus H3. So if it's with regard to the moisture content, then instead of H we use the W. However, I'd like to express this in terms of this expression, which I think we'll be using this expression directly. Right, so from this we can use maybe H3 is equal to MA1 H1 plus Ma2 H2 all over Ma3. Right, so that's for the right, so that's for the H3. And for the humidity ratio, we have Ma1, of course, times, instead of H we use the moisture content plus Ma2, right, divided by Ma3. Right. So this will be our working equation later on, but sometimes it's expressed in terms of this because it somehow shows that the ratio of this mass flow rate is equal to the ratio of this, or the average or something. But anyway, you can do the math. But for us in our computation, I think this one will be handy, because sometimes we're asked to find the enthalpy of the state 3, or the moisture content of the state 3. And so if we can have, or if we have this, or we have these two properties, then therefore we can find the other properties, right? So this will be the W3 and this will be the H3. Right, so once we have the two properties, then we can solve for the other properties. Right, so I think anyway, I'm not sure if the frame moves, but this is the equation I was talking about. So for the H3, here it is, and for the moisture content, here it is. Okay, so now let's do a sample problem for this topic. Okay, so it says here 1/2 cubic meter per second of air at 15 degrees C dry bulb and 13 degrees C wet bulb temperatures are mixed with 0.2 cubic meter per second of air at 25 degrees C dry bulb and 18 degrees C wet bulb temperatures. Determine the dry bulb, wet bulb, and the dew point of the mixture and the enthalpy of the mixture. Right, so first step again is to, so number one is to plot and obtain necessary data. Okay, so to plot this, we have 15 degrees C. And so 15 degrees C dry bulb and 13 degrees C wet bulb. So here's the 15 degrees, and we have 13 degrees wet bulb. So here's the 10, 11, 12, 13. So it is. So here's our, let's say, state 1, and for state 2 we have 25 degrees C dry bulb and 18 degrees C wet bulb. So 25 and 18. So 25. Then 18. So 15, 16, 17, 18. Alright, so here's our state 2, and therefore for the straight line, for the mixture, it's gonna be something like this. Right, so the point 3 would be somewhere right here, somewhere in between. so next is let's obtain the values. This is approximately 0.008, let's say 0.0084, 0.0084, 0.0084, and for this is around maybe 0.014, maybe 0.014. This is W2 and this is W1. And for the enthalpy, we have let's say H1 is equal to 37 kilojoules per kilogram, and right here we have 50 kilojoules per kilogram. Okay, so to do that, to find the moisture content at point 3 and the enthalpy at point 3, we'll use the equation. So H1 H2 0.014. Zero zero 0.084. Okay, and for the H1, this is 37 and 50. So this is 37 and 50 kilojoules per kilogram. Kilojoules per kilogram. This 1 kilogram water per kilogram air. Okay, so next one, I think we also need the flow rate. Right, so for the flow rate, this is maybe around 0.86 or 0.86 for the mass flow rate. And right here, this is maybe 0.825. So V1 0.825 cubic meter per kilogram, and this is 0.86 cubic meter per kilogram. Okay, so now the next step is to solve for the mass flow rate. Okay, so for the mass flow rate, we have MA1 is equal to the volumetric flow rate divided by the specific volume. This is 1/2 cubic meters, so that's 0.5 cubic meter per second divided by the volumetric flow rate, specific volume of 0.825 cubic meter per kilogram, and this is so 0.5 divided by 0.825. This is 0.6. So 0.6 kilograms per second. For the mass flow rate, for the second airstream, this is the V total, of course, at point 2, and the specific volume at point 2. This is 0.2 cubic meter per second, and divided by the volumetric flow rate of specific volume of 0.86 cubic meter per kilogram. This is 0.2 divided by 0.86. This is maybe 0.23. 0.23 kilogram per second. Okay, so next is, since we now have the flow rates, then we can solve for, right now we can solve for the mass flow rate of the mixture. Flow rate of the mixture. So MA3 is just simply equal to MA1 plus MA2. So 0.6 plus 0.23 is equal to 0.6 plus 0.23, 0.83. This is kilograms per second. Right, so next step is, since we have this MA3, then we can solve for or calculate the moisture content of the mixture. So the equation will be this. Just simply MA1 times the moisture content at 1 plus the water vapor at 2 divided by the mass flow rate, total mass flow rate. So if you substitute all this, this is 0.6 times 0.0084 plus MA2 0.23. 0.23 times this 0.014. And therefore this one is approximately, or let's compute, or divided by 0.83. 0.6 times 0.0084 plus 0.23 times 0.014 divided by 0.83. This is equal to 0.009, or we can just write 0.1 kilogram of course water per what's this, per second. Okay, so next one is okay, next one is to calculate the enthalpy. Enthalpy of the mixture. Right, so for the equation we have H3 is equal to MA1 times the enthalpy at 1 plus MA2 times the enthalpy at 2 divided by MA3. This is 0.6 times H1. H1 is 37 times 37 plus the MA2 0.23 times 50 divided by 0.83. If we do this, 0.6 times 37 plus 0.23 times 50 divided by 0.83. This is 40.6 kilojoules per, this is seconds, so kilojoules per second. Therefore the properties of the mixture will be, so dry bulb, wet bulb, and the dew point temperature. We have 40.6 kilojoules, so somewhere here 40 point, so it's somewhere right here, 40.6. So the picture will be somewhere here, right? This is 0.3, and for the humidity ratio it must be in between. We have 0.01, so 0.01, so it's close to this. Okay, so I think it doesn't fit, so maybe we can check. Anyway, you just have to check it out where we missed, but the process is actually the same, so it's almost like that one. So I think that's all for our topic in this psychrometry, and in the next topic we'll be discussing the ventilation rates. So see you in the next video.